20 past the hour. We're well on time. In a minute, you'll see one of our factories. English Electric, that's my firm. I served my apprenticeship on traction work. Oh yes, we build locomotives. You're riding now behind one of our diesel-electric locos. We produce the whole job. Diesel engine, generator, traction motors, control gear, bodywork, the lot. In those days, of course, the main lines were still steam-worked. No, you won't find many drivers wanting to go back to steam. By modern standards, the steam locomotive is a primitive machine with a service efficiency of only 5 to 6%. Today's electric and diesel-electric locos can improve on that 3 or 4 times. We've come a long way, even since my young days. The modern locomotive is, in fact, the product of many different trades and skills, some of them highly specialized. As you know, we are a very big concern, with 24 major factories in Britain and with works in 6 countries overseas. After all, we make everything, from large power stations to domestic washing machines. Diesel engines and electrical equipment for locomotives are made at Preston. All this work has to be dovetailed together, and that's the job of our traction engineers. We've been in the traction business since the beginning. Our organization includes the original company formed in 1823 at Newcastle upon Tyne to build locomotives, and George Stephenson's son Robert was senior partner and manager at the age of 20. It was there that the rocket was built for Stephenson's Liverpool and Manchester Railway. The line whose opening in 1830 launched the railway era in earnest. We also have the Vulcan foundry built by Robert Stephenson and Charles Taylor, close to the Liverpool and Manchester line. Here a continuous tradition of locomotive building has been maintained since those pioneer days. Now, of course, the age of steam is passing. The large-scale generation of electric power and the rise of the internal combustion engine has provided a more efficient means of locomotion. While steam is still required for electric power generation, steam locomotives began to give way to electrification. Chief among the companies that pioneered electric working in this country were Siemens of Stafford and Dick Kerr of Preston. Between them, they supplied most of the equipment for the electrification schemes that, from the end of the last century onwards, were replacing steam services in the more densely populated areas. Both these firms became part of the English Electric Company in 1919, and we became the largest manufacturers of electric traction equipment in Britain. Electric working is ideal for suburban traffic, but when it comes to lines that link cities across hundreds, maybe thousands of miles of thinly populated territory, complete electrification isn't always economic. In such conditions, the modern answer is the diesel-powered locomotive. One of my jobs as a traction engineer is to travel out with a team of experienced men to any part of the world from which we have an inquiry for locomotives and bring back a detailed report of the situation. You know the sort of thing: terrain, altitudes, gradients, curves, weather, temperature variation, dust intensities, and so on. Our report is then studied by our engineers at home, who decide upon the size and type of locomotive most suitable for the projected job. This report is sent to the railway administration concerned and can be used as a basis for its worldwide call for tenders. You can say of our type of work that no 2 assignments are ever precisely the same. Each one requires a new set of calculations. This is a monumental job, or it would be without computers to help. We have a large, extremely complex computer installation which takes on the more elaborate work. A smaller computer is used to solve most of our traction problems. Naturally, no computer can do our thinking for us. It can only do the sums. We must first work out the basic figures relating to distances, track conditions, timetable requirements, tractive effort, fuel consumption, weight, speeds, and anything else that comes into the picture. What the computer does is to put all these figures together and return us the correct answers without our having to wait. Our traction engineers take the answers and translate them into practical form. At this stage, we're concerned only with the general layout and main details. Preparing the tender may take several weeks. As soon as we get an order, a program for manufacture is drawn up. A typical contract will need anything up to 5,000 working drawings. We design the whole locomotive, inside and out, to the requirements of the railway concerned. But although tailor-made, it will incorporate many components which have been standardized. Engines, for instance, motors, control gear, and so on. The advantage of using standard equipment is that it has already proved its reliability and use. And when our overall design is ready, the drawings go out to the departments concerned and production begins. Engines are the source of power in diesel locomotives. We use our own engines, which are designed for traction work, a robust medium-speed engine of cast alloy iron construction. The first of them went into railway service more than 30 years ago. Now we have several thousand in use throughout the world. There are more than 2,000 of our engines in service in British Railways locomotives alone, which is probably the largest number of locomotive diesel engines ever supplied by one builder to one railway system. Steady development throughout the years has increased the rating of our engine from the original 50 horsepower per cylinder to nearly 200 horsepower per cylinder. The engine is made in 4, 6, 8, 12 and 16 cylinder combinations, so that there's a complete range of engines to meet all the locomotive requirements of a railway, whilst maintaining interchangeability of line components and wearing parts. The criterion of a good engine is reliability coupled with low maintenance costs, and this we've achieved. Power is transmitted to the locomotive wheels through generators and traction motors. For reliability and compactness and low maintenance, there's still nothing better than a well-designed simple axle-hung motor. Tests have shown that even at speeds of 100 miles an hour or 160 kilometers an hour, track stresses with light axle-hung motors are little, if any, greater than with complicated and expensive, totally spring-borne motors. We have over 27,000 axle-hung traction motors in service, including those performing one of the most arduous duties in the world on British Railways 3,300 horsepower diesel locomotives. These motors each average about 300,000 kilometers running per year at speeds up to 160 kilometers an hour. Meanwhile, the framework and superstructure of the locomotive has also been taking shape. underframe with its pipework and conduits for air, water and electric cables. Then the body framing, which is built up of steel sections by welding. The body is panelled and the equipment installed and connected up. This then is our system in operation. We have brought under a single administration the whole range of specialized skills and techniques that go into building a locomotive. Throughout the production of a first order, the railway company's representative will be there, living with the project from day to day as we live with it. He shares our vigil at the final testing, keeping a close watch on every operative detail. Detailed and rigorous tests are completed. Now she moves out of the factory to take her first run in the open. The test track at the Vulcan Works is unique of its kind. It's built to 4 different gauges laid out round a sharp curve on a gradient of 1 in 42. An overhead cable for electric locos can feed in current at any voltage, AC or DC. Special plant installed beside the track can simulate the effects of severe dust and rainstorms. Rail gauges differ around the world, and for this reason, if for no other, many of our locomotives must travel to the docks by road. Our responsibility doesn't end, however, when we've delivered the locomotive. With every first order, we send out a team of site engineers to remain with the new locos during the first 12 months of operation, to help the customer in every possible way. Their first job is to assist in commissioning the locomotive. Instruction is given to maintenance personnel in the operation of the locomotive and on maintenance procedures. Complete details can be supplied of maintenance sheds, showing their layout and the equipment required. The correct handling and driving technique is demonstrated. Experience has taught us to deal quickly with any teething problems that may arise when the locomotive enters service. The locomotive builder must make reliability his first objective. Don't forget that one fault on one loco may be enough to disorganize the working of a complete railway section. Reliability is one of those basic elements that must be built into your design. You can't stick it in afterwards like an extra nut or bolt. This was the sort of thing I had in mind when I was talking about our policy of standardization. Another objective is economy of operation. The designer must anticipate the range of different duties which his locomotive will be called upon to fulfill, and see that it will serve them all with a minimum of wastage. In this respect, the flexibility of electric and diesel-electric operation has many advantages. Well, yes, sir, multiple working, for example. 2 or 3 units can be run as one without loss of efficiency, under the control of a single train crew in their cab. Furthermore, this type of power requires far less time than steam for fueling and maintenance. Given normal conditions, our diesel-electrics show an availability rating of over 90%. Those are good figures, but like everything else, they have to be planned for. Simplicity of function is a basic aim in all our design work. The simpler your mechanism, the less likelihood of trouble. For example, our control cubicles need only simple maintenance at 3,000-hour intervals, and our engines run over 20,000 hours without top overhaul. We're proud of the number of repeat orders we've secured. Between 1957 and 1964, 90% of the mainline diesel locomotives exported from the United Kingdom were built by us. On many overseas railways, we have pioneered these forms of traction. Take Africa alone. In the last few years, over 400 electric and diesel-electric locomotives have been dispatched to that continent from our works. We've supplied locomotives to countries all round the world, for service in every variety of climate and duty. New Zealand, with its steep gradients and highly curved tracks. Malaya, facing the climatic extremes of the tropics. $1,500-ton loads being hauled across the deserts of the Sudan. Australia and its great distances. Giant electric locos hauling coal and iron ore through the Spanish mountains. The crowded trains of India. At home, much the same story. We have supplied to British Railways about 800 complete diesel locomotives, as well as equipment for more than 1,200 shunters and nearly 3,000 electric trains. When the first British mainline diesel-electric started work in 1948, the power equipment was ours. In 1934, we equipped the first diesel shunting engines in this country. Back in the 1890s, we pioneered the transition from steam to electric working on suburban and underground lines. And before that, well, as I told you, our story goes back to the dawn of locomotion, earlier even than the rocket. In a nutshell, it spans the whole period of powered railway operation. From this to this.